Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Welcome to episode 64 of the Reliability Matters podcast. On this episode, we'll have a conversation with two industry experts on the subject of solder voiding mitigation and oven profiling, two subjects which both influence solder voiding. This will be a two-part episode. Today, we'll dive into void mitigation and how vacuum reflow technology can help reduce or eliminate voiding. Part 2, on episode 65, coming up in 2 weeks, we'll discuss profiling best practices. My guests today and on the next episode are Tim O'Neill from AIM Solder and Fred Dimock of BTU International. Tim will discuss voiding mitigation from a material standpoint, while Fred will cover equipment and profiling strategies. Tim O'Neill is the technical marketing manager for AIM Solder. Operating out of AIM's U.S. headquarters, Tim is responsible for developing and optimizing product and technical information, collaborating with complementary suppliers and equipment manufacturers, and ensuring AIM's products exceed expectations and meet market requirements. Tim is also a technical writer and presenter for industry trade publications and events. He has co-authored several papers on PCB assembly subjects. Tim is also an IPC-A-610 Certified Specialist. Fred Dimock is the manager of process technology at BTU International and recently started a consulting business, FCD-Global Services. Fred holds an associate's degree in mechanical engineering from Wentworth in Boston and a bachelor's degree in ceramic engineering from the State University of New York. Fred has also authored numerous articles on lead-free solder process control and operation of continuous furnaces. His papers have been published in English, Chinese, and German. He has taught numerous SMTA solder reflow classes and participated in the 5-45 subcommittee for the development of IPC-A-610 Reflow Oven Process Control Standard. Additionally, he wrote the chapter on solder reflow for the Handbook of Electronic Assembly, a guide to SMT certification by Dr. Lasky and Jim Hall. Fred received distinguished speaker status at SMTA Guadalajara, Mexico, and is a key presenter for the SMTA Jumpstart program for new engineers. This episode is available in both audio only and a video format. To view the video, complete with Fred's informative slide deck, visit our Reliability Matters YouTube channel. Now here's my conversation with Tim and Fred. Tim O'Neill, Fred Dimock, welcome to Reliability Matters. Thanks for being my guest today. Tim, thanks for a second round with me. This is your second appearance on this show.
Thanks for having me.
Yeah, thank you for inviting me to be a part of this. This is exciting. I like to do these sorts of things.
Tim, your stuff is what goes into his oven, so you're equally to blame, or you can equally take credit for the successes. So it's long been said by many that pretty much all reliability problems start at the print process. I'm going to kind of just shove that 1 degree down the river and say that reflow has just as much to do with it, because after all, you're reflowing what has been printed with whatever materials they've been printed with. So I think between the printing, the material selections, and the reflow process, that's pretty much going to set up the success or failure of a circuit in the future. So I think this is a valid and timely topic. First, before we get started, Tim, you're with AIM. How's AIM doing in this whole COVID debacle that we're going through right now?
I think you mean the upside down world. In the upside down world, AIM is doing very well. In fact, I think I would speak for a lot of my colleagues in this industry that electronics have done fairly well, and I think it has a lot to do with the investments people are making in their home offices, the advancements that are taking place in automobiles, connectivity. All of these things revolve around electronics manufacturing. So the pandemic has actually increased the demand for a lot of these devices. So our industry, thankfully, has been somewhat unscathed So we are on an upward trajectory, and in fact, I would say we've probably had a little uptick in activity due to the changes in the market.
Excellent. And Fred, how's things at BTU?
Very, very much along the same lines as what you heard from Tim. We've seen things really continuing to move forward. Since we're talking basically about the SMT side here, that stayed very strong with us for us. We're seeing customers being very active, but also we have a second part of our business, which is the high temperature furnaces, and that hasn't slowed down either. I mean, that's just there are a lot of people talking about replacing furnaces. There are a lot of people replacing furnaces. There's some new people getting involved in the industry. So we have seen very little slowdown as itself. But us in doing the work gets to be a little bit harder because some of us are forced to stay home. It's been hard to do some traveling. We've learned how to use a lot of the electronic, the things that are available to us. A lot of online conferences. So again, it's changed the way we do things just a little bit.
Yeah, I've long commented that for an industry that is a highly technical industry, we build the things that make the world work. I think we're a little behind when it comes to all the familiarities with digital communications, Zoom meetings and things like that. I can't tell you how many meetings I've had. Because we're all old. That's probably it. Yeah.
Exactly. The younger guys have a very easy time going in and using them. Like Tim suggested, we're old, but you can teach us old dogs new tricks.
Well, we clearly have. My mom is 83 years old, and every once in a while I'll get a little frustrated because she'll call me and ask me how to do something on the computer technical, and it's kind of a long process to walk her through it. And then I have to pause and go, she's 83. She's on Facebook. She's on Instagram. She Zooms. She's 83. So yeah, I have to put everything in perspective. So let's talk about Reflow, and I'm going to ask. I'll throw it out to both of you. Whoever wants to jump into the fire pit first is welcome to. What are the most common issues? And I'm not going to let you off the hook there. And solutions encountered during Reflow.
Oh, I would say that. Yeah, I'd say that currently, and I think Tim may agree with this one, is that the current issues that we're hearing most about, I think, is voids. There's a lot of that going on, and there are a couple of solutions that we see that are in that area. One of those is the low voiding paste, and the low voiding paste really allow people to get down to a bit lower level in voiding. And then the other part of that is something that needs very, very low, very, very low voiding. And then we go to vacuum reflow. Is this a good time to talk about vacuum reflow?
It's never a bad time to talk about vacuum reflow, Fred.
Okay.
Do you want me to share? You want me to put your slide deck up?
Sure, you can do that.
Here we go. Okay.
Okay. The void issues, and the first slide talks about the void issues, and really what we talk about is the thermal management of QFNs, and that's basically about keeping the chip cool by eliminating voids, because empty spaces in thermal pads don't transfer heat. And now they aren't really empty spaces, and I talk about them by empty spaces because early in one of the trials that we're doing, we talked about vacuum reflow as being something we use nothing to remove the empty spaces. Vacuum being nothing, the empty spaces, being the voids. But really, the empty spaces predominantly end up with flux in them, and flux doesn't transfer heat as well as the metal does. Recently, we've heard people with working with high frequency signals talking about voids affecting what goes on in the connections. that it seems to distort the frequencies, and people are a little concerned about that. What we know is that typical reflow results in about 40% voids in thermal pads. That's been fairly well known. And when people first began talking about voiding, I had a lot of hope that guys like Tim and his team would be able to come up with low voiding paste that would really get the void level down dramatically. Okay, and we've learned that low voiding paste does work. They've been able to. I've heard people report on getting down to from that 40% that we'd normally see down to the layers of 15%. I've heard some people talk about 10% and down to even 5%. But really,
Fred, let's make this a little interactive. I want to only pause because I want to get Tim collated into this conversation. You had said that that the solder paste manufacturers have come up with different formulations to reduce voiding. Tim, what are you doing? How are you doing that?
Well, there's some realities that we have to contend with, and the most important one is the fact that solder paste is approximately 50% flux by volume. So the printed deposit on that pad, once it's reflowed, half of it's flux and flux residue. So how you manage the amount that is volatilized during the reflow process and how you can get it to move places that you want it to is our role, and that involves the solvents that are used, the alloy that's in use can have an effect, the wetting forces, and all of these things interplay with the profile. And I want to you can't overstate the importance of profiling and the oven technology in terms of outcomes for all defects. I have this mantra that I say, and it's simply that the only place on a production line where the output can be manipulated in real time is the oven. So let's assume at the printer we have our stencil design dialed in and it's perfect. So that means that the amount of solder paste is well controlled. It's in the designed pattern and the exact location where we want it to go. That's a perfect printing process, but it's static. Once those variables are fixed, you have to actually go and get a new stencil in order to change them. So there's not much you can do. The solder paste is fixed. It is what it is. Placement, once that's optimized, then you're putting the component where it's supposed to be, orientated correctly, with the right amount of pressure and the right amount of depth. That's fixed. So what can I do as a solder paste manufacturer to change an outcome? And that's all in the oven. So, voiding is, I agree with Fred, voiding is probably the most commonly discussed subject. And one of the reasons is because it's so difficult to resolve satisfactorily.
It's certainly one of the most discussed things on this program.
For sure.
I think voiding comes up like every 3 episodes or so.
It's hard to fix. We wouldn't be talking about it if there was an easy solution, right?
Sure.
We'd have fixed it by now. And there isn't one. But other common issues that we address with the oven and two that come to mind are wetting issues. So we can manipulate the way that a solder paste wets by restructuring the profile. There's, certain families of profiles. We call them linear profiles, or ramp to spike, or ramp soak spike, and then you can manipulate the soak to a high soak, low soak, long soak. And these are all strategies that our technical staff is well versed in, that they can assess a assembly's thermal characteristics and then deploy these strategies that have proven to have a desired outcome in order to get the customer the result that they need. And then finally, residue, the amount of residue, the location of the residue, the consistency of the residue, those things can all be manipulated in the profile as well. Keeping in mind, there are limitations. I mean, the profile, if the paste is in some way compromised, or the board's in some way compromised, or the components in some way compromised, profiling can address some of the issues, but it's not going to fix a glaring issue. It's more of a nuanced corrective action than a dramatic corrective action. So profiling, super important and often neglected.
Right.
Yeah,
Thank you. Thank you for that.
We as the furnace guy really have to count on people like Tim to tell us what the profile needs to be, because it is so complicated. And that's really where it comes. That's where the low voiding paste comes from, and what the thermal profile is. But the issue tends to be that people don't truly understand what level of voiding that they can withstand within the thermal pad. And that's why I got to put the note down there that says voids are still higher than desired. So why don't you flip to the next one? Let's see. Okay, so
no void is a good void is another. We just don't want any voiding.
Right. Mike Malonis at the Area Consortium out of Universal did this study a bit of time ago. I worked very closely with Mike. He showed that on MFL 100s, the standard no cleans were up at about 33% in air, and then as he went down through low voiding paste and air and nitrogen and changed the profiles a bit, he showed that he could get down to about 10% with a very hot profile in nitrogen. You can see the two X-ray images there. What a 33% voiding looks like, and what a 10% voiding looks like. And it's still interesting that even at 10%, it looks like there's a fair number of voids in there, and some of them are fairly large. If you flip over to the next one, okay, so the question is, why vacuum reflow? Well, we know that voids are formed by the flux resonance in the outgassing of the flux. They grow by merging together, and that's a big if, they contact an exposed surface, they escape the solder. That's how they come out. Large voids are more likely to contact that surface than disappear. Okay? Vacuum reflow actually uses Pascal's law. So what happens is you lower the pressure, the voids get larger, and the larger voids have an opportunity to combine and become even larger ones, and then contact the surface. Also, what we've seen is when you put a vacuum on a joint, what happens is the voids tend to move around a lot quicker. They tend to be a lot more mobile, and then that again has the opportunity to combine. If you jump to the next step, there are four basic parts of the vacuum process. Okay, one is pump down, and this doesn't include transport in and out of the chamber. The pump down is really the rate at which the vacuum is applied. What we found was if the rates were too high, we ran into issues. One of those issues was there's the voids come out of the paste. They come out catastrophically. They almost explode out of the paste if it's too fast. What happens then is you end up with solder balls and splatter. And we even found that at very high pump down rates, we could take an MFL 100 and flip it over on the board. Absolutely just turn it over. It was amazing to see that. The vacuum level is the level you go to. That's usually in torr. Hold time is in seconds. And then when you get through with that cycle, you need to return things back to room atmosphere so you can get this chamber open. This chamber actually sits in a reflow oven, in a hot section of the reflow oven, just before the cooler. So it's in the oven, and it's working in that hot section of the oven. If it's a nitrogen oven, which most of them are, this is actually within the nitrogen atmosphere in the center of the oven. If you flip to the next page.
Let me ask you, Fred, an
Sure.
ignorant question, if you don't mind. I love asking ignorant questions.
Oh, no, there is no ignorant question.
Oh, yeah, you don't know me well enough. So to draw a vacuum, obviously it has to be a sealed environment. So I'm guessing, unless there's some miraculous technology out there that I'm not aware of, that a vacuum reflow process is more of a batch process. Is it actually conveyorized? Is it completely batch? Is it hybrid?
It's basically a hybrid. What we do is we take a standard convection reflow oven and put a vacuum chamber between the last heated zone and the cooler. It's actually inside the oven. the vacuum chamber is an elevated temperature because you need to keep the board hot and keep the solder molten for that to work. So it actually sits inside. There are two types of chambers. One's a bell jar design that actually just is a typical bell jar. You raise the cover, you raise the top of it up, put the board in the chamber, lower it, and then go through that pump down cycle. The other one actually has two doors, one on the entrance and the exit of that area. You do have to stop the board when it's in the chamber during the pump down.
That's what I was going to ask. The conveyor has to stop, right? Because it has to form the seal. So when the conveyor stops, what's happening to the boards before the vacuum part? Are they just stop? Are they just baking in one place, or what happens there?
No, that if we had to do that, it would really affect the profile. What we do is we have a transfer. So the typical conveyor in the oven runs continually. In our case, when it gets to the vacuum chamber, it actually goes down underneath the vacuum chamber and back up. There's a transfer between the conveyor that's in the oven to the vacuum chamber. So there's a separate conveyor inside the vacuum chamber. And then what it does is actually stops the board in the chamber while it goes through the vacuum cycle. That means there's sensors in there that have to work at a very high temperature. And some of those are up at, some of those temperatures we run in the vacuum chamber is close to 300 degrees C. So that's some significant, let me tell you, I'm impressed with the sensors, okay? There's also a seal that has to work at this high temperature and with the low vacuum. So that seal is really very important. The materials that are in that, and then that does mean though that you cannot put the boards right next to each other when they go through the reflow oven. They have to have a space. And what we use SMEMA and some timing on SMEMA for when the next board is allowed to come into the oven, so that we don't run a board into a closed chamber, or that we don't have a board within the seal area when the chamber comes down, because you certainly do not want to ruin that seal. Those seals can be very expensive.
Yeah, well, very interesting. Thanks for sorting out the flow diagram in my head. Tim, before we let loose Fred again to continue his presentation, any input on vacuum reflow from a material standpoint?
Well, I was fortunate enough to work with Fred on some of this. I've actually seen that oven in the APL lab at Universal Instruments, and it is quite an impressive piece of equipment. It's almost what I would cliche. It's space age. It's got all of the literal bells and whistles. But no, vacuum reflow voiding, there has to be a good reason to need voiding to go to that level. We are continuing to develop our chemistries to reduce voiding levels. In fact, we're going to be releasing a product in Q1 that specifically addresses voiding, hopefully better than its predecessors. I'd say the numbers, there is the IPC Rev H just came out with a 50% voiding maximum as an advisory. It will become a specification, I presume, even though it's not a specification technically, but it's a advisory. And I think it'll be driven by customer requirements regarding the heat transfer that Fred mentioned. So while a 50% spec will address most of the industry's requirements, obviously there's going to be applications that's unacceptable, and they're going to have to come up with their own level of voiding. It isn't just QFNs that are affected. We have clients, particularly in the automotive arena, that have maximum void levels for other components as well. So we know about BGA. There's a 30% max spec, which is different than an advisory on the IPC. But then we have other clients that have maximum void levels for all components, including leaded devices and chip caps. So voiding, I think, has been vilified, perhaps unnecessarily. I think it is a proverbial red herring when it comes to some of the failure mechanisms that are out there. But the fact that you can see it and you have a failure, the correlation's very difficult not to. It's very difficult not to conclude that the voiding is somehow responsible for the failure mechanism. So I think we're going to have to live with this desire for low to no voids forever and ever.
And we've said on the show before, clearly before we had X-ray, we had no voids and X-ray. So clearly X-ray causes voiding. So gentlemen, from another ignorant question, from a failure analysis standpoint, voiding, what's the biggest failure caused by voiding? Is it an inferior bond, an intermetallic bond? So, a joint can just break off if there's not enough solder volume underneath. B, heat dissipation, lack of heat dissipation, and the part overheats and burns up. Or C, not enough current can get through a smaller solder connection. Or A and D, any others. Or A, B, C, D, E, all of the above. What's your take on that?
Mostly what we hear about is B, that's heat dissipation, because that's the thermal pads. But we're also hearing people again about in the high frequency market, high frequency area, thinking that voids do affect what goes on in the leads and in the lead area. There have been some reports out though that say that voiding actually, how to say this. Voiding, the presence of voids actually helps stop cracks that would go through a solder joint because they interrupt the cracks and they actually make the effect of the solder joint a little bit stronger. And I have heard that numerous times from people.
So you heard it here first. Improve reliability. Add voids. Tim's formulating a high voiding paste right now.
Right.
I got a few of those.
It's the size of the voids, I think. But we are hearing a mixed bag from where people need to be in voiding. I mean, it tends to be all over the place. We still do have people saying that they need less than 5% voiding because of thermal conductivity. A lot of it comes in with the automotive people that want to put higher power in the chips, and what they want to do is have the minimal amount of voiding. I'll talk a little bit about voiding, about percent voiding a little bit later as we go along. But we are continuing to hear that. But like I say, the voiding that they talk about is kind of all over the place. I would say that in general, I think we're predominantly hearing less than 10% voiding is what people want.
There's another failure mechanism. When I was doing my ABCD, there's an F also, F for failure, and that goes into the electrochemical migration world, which is dealt with by the cleaning industry. People when they hear the term void, we think void means nothing. It's void of anything. It's only void of solder. And Tim, I think as you mentioned earlier, there's flux in that void, and that and typically that might be unactivated flux. It might be activators, bad actors otherwise. And if you have a lot of voiding, there's a pretty good chance you have a lot of entrapped flux activators or some flux components within that void, which is what caused the solder not to reflow there. So, and that's depending with the proliferation of bottom terminated components, depending on a lot of other factors, that's created an issue in the ECM reliability world, electrochemical migration, where we're seeing failures because of the volume of flux or flux activators or some form of bad actors within that void area. Any comment on that, Tim?
I don't know if it's isolated to the void area specifically. I think it's an issue that's been realized with low standoff devices becoming more and more widely used. What the data has shown, and my competitors and as well as ourselves have done a fair amount of study on the phenomena when you smother, for lack of a better term, flux residue, the electrochemical properties are affected, and generally adversely. So any low standoff device, void or no void, that's a consideration. It's something we're working on to develop higher, well, in concert with that, SIR requirements, surface insulation resistance testing requirements are becoming more and more strict as well. Fred mentioned the automotive industry. They drive a lot of, pun intended, they drive a lot of what happens in terms of product development and research. And they're doing 1,000-hour, 2,000-hour, and 3,000-hour life cycle testing on materials. And, that's putting pressure on the suppliers of all the materials to develop things that can withstand these more aggressive, longer test cycles, which can result in things such as electromigration occurring where it would not have been detected on a B-24 coupon in an open atmosphere.
Very good. Fred, I'm going to go back to your presentation, and then I want to steer the conversation toward profiling, if I can, because I have some questions about profiling, and I have a few in my world, in the cleaning world, where my day job, the profiling is actually quite important because the lack of proper reflow temperature can fall into a cleaning problem later. But we'll get into that in a little bit. Let's go through the rest of your presentation here.
Okay, if you can go to the next slide, that would be helpful. There we are. This is an explanation of a trial that Tim mentioned that was done at the Advanced Process Lab at Universal. This is a copy of the board that we did. We had a whole bunch of different components on the board. We did it in air and nitrogen, number of different paste, SAC 305, Interlot, tin lead, had 3 paste suppliers, plus one more, which was Tim, and I'll explain that in a second. 2 board furnaces, a couple of pad designs, some with vias, and we varied the vacuum level in the whole time. We ran well over 200 boards with multiple data points from each of the boards to develop an understanding of what really went on during vacuum reflow. I'll come back to the comment about Tim, that other paste supplier. Tim came in and we ran some of his paste through on this particular board. We did a quick analysis of that. We don't have a lot of statistics on that because we only ran a small number of boards through, but we were very surprised at how good the paste that AIM had responded to the vacuum reflow. They were at the lower end of the voiding of what we had seen. And to us, it was surprising. Tim asked me if he could use this in marketing campaigns later, and I was kind of hesitant to allow that to happen, only because we didn't have an awful lot of data, a lot of statistical data to back it up. But yes, it was real. We were amazed at how good the AIM solder paste was in the vacuum. Okay, if we run to the next,
not to rain on the AIM parade, but does the use of put your umbrella up, Tim. Put your umbrella up for a moment. Does vacuum reflow widen the spectrum of useful solder pastes? In other words, if there's a solder paste that's known to be fairly high voiding, when it is used in a vacuum reflow process, will that lower the amount of voiding? Does every paste perform better or in a vacuum reflow environment, or are there still needs to have specific formulations that would somehow take advantage of the vacuum reflow process? If that question makes sense.
No, that's a very good question. I would say that vacuum reflow works with it helps lowers the voids in any of the paste that people are using. One of the reasons that the automotive folks are very interested in vacuum reflow today is that they can change to vacuum reflow in their process line and not have to change the paste. And what happens is they've spent a large amount of time qualifying their process and qualifying their materials, and for them to change the paste to low voiding paste would take a large amount of qualification. They have to start all the way over from the beginning. I mean, it's not something where they can do within months. It's something that takes years. And what they can then do is they can just switch over to vacuum reflow and not have to go through the massive qualification process. I mean, that's one of the things that's driving vacuum reflow.
For my audience sake, I don't want to get into brands and prices, but just as a generic statement, let's put it in a percentage standpoint. Percentage-wise, how much extra does it cost for vacuum reflow compared to standard convection or whatever? Is it a 50% increase? Is it 1,000% increase in general? What are people paying for the advantages of lower voiding through vacuum reflow?
I'm guessing in the range of 50%, 50, maybe even 75% more. And part of it is that that vacuum chamber and vacuum pump is not inexpensive. You're adding it to a reflow oven. You're adding this large amount of cost to a reflow oven. So yeah, it is expensive. I'm saying 50% plus.
Not just the pump, but Tim was calling it a very space age looking machine. There's a lot of moving components, right? Conveyors that move boards around and pull them aside and put them in a vacuum chamber and things like that. Okay, let's go. Sorry, I've diverted you.
Yeah, that's okay. Another part of that is that because of that, because people don't want to have a line that just runs through vacuum reflow, we have the ability now to do what's called a pass-through mode. And what that does is the oven acts like a regular oven, a regular reflow oven, without having to go through the vacuum cycle. So what we do is have actually heat in the vacuum chamber so that it acts like a regular oven.
Okay, great.
So that does help. That does help the cost a little bit. And in that case, you don't need to separate the boards. It can act like a regular. Normally what we do is put this in the frame of a 12 zone oven. So we have 10 zones of convective reflow, and then the vacuum chamber, and then the cooler. And they are in line. We don't take them off to the side. We keep them directly in line.
Okay, great.
Okay, so if you show the next slide, this is just shows some results from that. This is the results, MFL 16s and 100s. You can just see the 16s are without vacuum reflow are on the left. The 100s are on the ones with vacuum reflow on the right. 16s on the top. The 100s on the bottom. And it doesn't take a rocket science to see that the voids have gone down significantly with vacuum reflow. This slide's a little bit more complicated than I usually like to show, but there's a lot of data here that's important to look at. If you look at the left, you see that there's a 760 torr, which is atmospheric pressure 0 seconds. That's without any vacuum reflow. We're at about 40% cumulative voiding. At even 245 torr in 30 seconds, we were down to 10% voiding. It took a very small amount of vacuum to really begin to start pulling voids out. As we went along with the lower void levels to the right at different times, you'll see that we got down to 5% and below fairly easily. But at about 20 seconds or so, we saw some scatter in the data at a few of the points. After we looked at the data, we found that we really liked the 30-second hold. That looked like it was the best. And this was on the larger components. This is the MLF 100s. If you go to the next page, right? Okay, this is the 30-second hold data. You can see across the top, there's no vacuum across the MLFs with 38%. The The 100s were 38%, the 52s were about 28%, and the 16s were about 20. As on the left-hand column, you'll see with lower vacuum levels, as we went from 500 down to like 6 torr was the bottom one, and this is all the 30-second data. You can see once we got down to that 20 torr, 30 seconds, we were down well less than 3% voiding in all the different components. You could see that the size of the component made a difference. It was harder to pull the voids out of the 100s than it was the 52s or the 16s. Okay, so that's just, matter of fact, that's the crux of the data that we had from that test. But let's go to the next page, because there's some things to think about when we start talking about voids. Okay, Mike Malunas and I. Mike was a gentleman who was doing the work out of the lab. We had a co-op that was with us, actually a postdoc, Arvin, and Mike and I were talking one time at lunchtime, and Arvin was with us, and we was talking to say, this thing about looking at cumulative voiding may be the wrong way to look at this. Okay, we really begin to wonder what would happen if we looked at small voids, and we kind of looked at the void distribution rather than actually the cumulative voiding. And you could see Arvin roll his eyes in his head because he knew what was going to happen. So we sent him off to do a project. And that's the next slide, shows the results of that. Okay, this is that same basic parameters across the bottom. We didn't do no voiding. And what we found is this is a void distribution analysis on the 100s. And what we found with 120 torr and below, the odds of getting an individual void larger than 2% was very, very small. At 60 torr and below, it was even better. And that's one of the things I kind of look at and really something that maybe Tim and I need to talk about sometime, is to look at the void distribution that we get from some of these low voiding solder pastes, because a small void may not make a big difference. It's the big voids that are probably making the difference in thermal conductivity and that thermal transfer.
I would agree with you, Fred. That was something that we actually had come up with an advisory for customers to silkscreen if it was possible, which was a big ask, but to silkscreen the bottom of the component into a checkerboard or a tic-tac-toe to not only provide a slight standoff that might help outgassing, but to also ensure that the voids weren't allowed to coalesce into one large area, and that they'd be broken up and distributed around the device in a more dispersed. So, yes, I would agree. Void distribution is a significant consideration. Now, that said, I'm not a PCB designer, nor am I a component engineer. So that would probably be somebody that we'd have to bring into this conversation to provide insight as to just how big a void can be until it becomes problematic.
Yes, maybe that's what we have to do, is take it on as a challenge to change the industry, or at least getting you to think about it. Yes. Okay. If you flip to the next page, it's just two more little pieces of data. Okay. The vacuum reflow oven, after it was at APL, ended up at American Competitive Institute, and that's where it is at this point in time. In November of 2019, we had a different set of boards that we did as part of the workshop, and what we did is put 2 boards down through a standard reflow oven, and then 2 of them down through the vacuum reflow oven, just to get a comparison of those. And you can see the pictures on the left show about 28% voiding without going through the vacuum oven, and the pictures on the right shows what happened at actually less than 1% cumulative voiding going through the oven. The interesting thing about this is that's a corner picture up there on the left showing some voids right in the leads. If you look carefully, you can see those voids. A few months later, I was back at ACI doing some work, and there was a customer with us. If you flip to the next page, okay, that customer said, "Gee, what happens if we take one of those boards that didn't go through the vacuum oven and looked at doing rework? Because a lot of people says, I did these boards and they failed voiding. Can I fix that issue? So what we did is we took one of the boards that was at the 28% voiding, cumulative voiding, and put that through the vacuum oven. And you see that on the right, and you can see the picture up there in the corner. There's almost no voids in those leads. And it tells us that, yes, you can take product that has voids in it and rework it. A number of people I've seen have done that actual thing now. We've done it for a couple of customers that need some help and want to save, a couple of dozen boards that are very expensive. You can put it back through the vacuum reflow oven. And that oven right now is at ACI, American Competitive Institute in Philly. And it's something that we do have available for demonstration purposes. ACI is a phenomenal group to work with, and that is available. Okay, I guess that ends that presentation, right? That's the end of that. But ACI is something, and Tim, I've told you a couple of times, you come on down.
No, I know ACI pretty well.
Yes.
Yeah, ACI is a spinoff from the EMPF, which used to be in China Lake, California, and then ended up in Philadelphia, and I think it's still operated by the Navy, or at least paid for by the Navy. Is that still the case? Yeah, right. It's a partnership.
Yeah,
okay,
they are a electronic center of excellence for the Army and the Navy.
Yes.
And the reason we like it there is because they've got screen printer pick and place. They've got a standard reflow oven, one of ours, vacuum oven, ours, and
which is why you like the place so much, Fred.
I like it. Yeah.
I see how it works.
And it's near the airport, so it's fantastic. You could almost walk from the airport to there.
Yeah, I've been there many times, and yeah, you're right. You can almost just drag your pulley, over there. Well, this is such an interesting subject. We're going to break this up into two parts. This is part one. When we come back in our next episode, we're going to dive into profiling from an materials and oven perspective, and we're going to talk about I love talking about things that could go wrong, that just is a little bit more dramatic. So we're going to talk about some of the common mistakes and misconceptions from your perspective, from an equipment perspective and a materials perspective. What are some of the mistakes people make when profiling in any oven, no matter how good an oven is? It could be $1 billion oven. It's certainly not going to produce reliable solder joints if the profile's not right. So an oven itself is only half the battle. Running it correctly is the other half of the battle. It was probably several halves, I guess. I'm bad with math. Probably several halves. So we're going to talk about some of the common misconceptions of profiling, and we'll get into prediction software. I think that's where a lot of the profilers earn their keep, is not just telling you what the temperatures are at any given point in time and location, but being able to run some algorithms that can predict an outcome and suggest settings based on input from Tim and Fred and others like Tim and Fred. And then I'm going to, on the next episode, ask you about what your predictions are for the future. So, polish up your crystal ball, put some Windex on it, get it nice and clear, and we'll talk about what you think the next several years are going to bring. And I think whatever the next several years bring, it's going to be critical with the electrification of automobiles and Internet of Things and connected factories and perhaps lights out factories and all of the things that IoT is bringing forward. Reliability is extremely important, particularly since the majority of these IoT devices are marching outside into harsh environments. Everything needs to be right. I think we're building boards today at very close to the edge of an envelope, and the right reflow process, the right material selection, the right profile in this conversation, the context of this conversation has never been more important than it is today. So, gentlemen, thank you for being my guest today. I'll thank you again in a couple of weeks when our next episode airs. And for those of you, for those in the audience that have been driving in their car envious of or suffering fear of missing out, suffering FOMO, because they weren't able to see all of these cool photographs and images that Fred presented, visit our YouTube channel. Just go to YouTube, search Reliability Matters, and you can see the video version of this podcast, complete with some pretty cool pictures of voids and other illustrations that Fred so kindly provided. So thanks again. I appreciate you all being here. Thank you for being my guest. Tim, welcome back. And in a couple of weeks, Fred, I'll say welcome back to you as well. All right, gentlemen.
Thank you, Mike. It was a real pleasure.
We'll see you in a couple of weeks.
Thanks, Fred. Bye, guys.
Bye-bye.
Well, that's another episode. Thanks for listening to the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on Apple Podcasts, Google Podcasts, Spotify, or virtually wherever you get your podcasts. A special thanks to Circuits Assembly Magazine's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. Thanks for your questions and episode suggestions. Please keep them coming. Send them right down here to my email address. Once again, thanks for listening. Stay safe, stay healthy, and stay happy, and perhaps most importantly, keep doing it right.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.